In this video, we're going to take a look at Taylor polynomials. Now, the idea here is that we're going to approximate a function with a polynomial. So we're going to build a polynomial that approximates some function pretty well around a specific location. And the reason why we would want to do this, especially back in maybe a couple hundred years ago, was that polynomials were a lot easier to calculate with and easier to deal with than other functions like e to the x power. E has this irrational base. E to the x power, excuse me, has this really irrational base. And so that would be pretty hard to deal with, whereas polynomials are pretty straightforward to deal with. Like I said, the overall idea is to approximate a function with a polynomial. So we're going to choose a function and choose a number, which we call C, the center. The polynomial should approximate the function well close to C. So in other words, at x values close to C, the polynomial and the function are going to be very near each other. The way we do that is we start out making the function value at C equal to the polynomial value at C. And then that'll match them up at C. In order to get them close around C, then we force derivatives to be equal at x equals C. So we're going to force the first derivative of the function to be the first derivative of the polynomial when we plug in C. So I start out by forcing the polynomial and the function to take on the same value when I plug in C. And then I forced the first derivatives to be equal when I plug in C. And then I force the second derivatives to be equal when I plug in C. And I do that up till I hit some value of n. And that value of n is going to be what degree I want this polynomial to be. So if I want a fourth degree polynomial, I will take and set the function equal, and then the first, second, third, and fourth derivative all equal. If I want the fifth degree polynomial, I do that up till the fifth derivative. If I want a seventh degree polynomial, I do that up to the seventh derivative. Let's take an example that's fairly straightforward, just so that we can demonstrate. We have the function e to the power x. In modern times, that function's fairly easy to approximate with because we have a lot of computing power in the palm of our hands, and that's perfectly okay. However, that function is this exponential function with a base which is irrational. So if I had to do a lot of things by hand, a lot of approximations by hand, it would be hard to actually calculate with e to the x. We're going to find a cubic polynomial, and we're going to center it at c equals 0. So we're going to let 0 be the center. Now, let me start out by saying this. When we want a third degree polynomial, oftentimes I will denote that with capital P sub 3. Sometimes I'll make it into a polynomial function by putting P of x is equal to. You can also just put polynomial equal to and get the of x part out of there. I'm going to write it from lowest degree term to highest degree term. So I'm going to write it in ascending order, which is a little bit atypical, but the reason for that you'll see momentarily. So we're writing a polynomial. It's got to be cubic. And when I say it's got to be centered at 0, that basically means we're going to have x to the first, x squared, and x to the third. The nice thing about this particular function, f of x is equal to e to the x, is that I know what happens at 0. And what happens at 0, actually, let me do it this way. What happens at 0 is I get a 1. Once I've done that, then I go and take the derivative of my original function. Now this one's very nice because the derivative, that is the first derivative, is also e to the x. When I plug in e of 0 or 0 into the function, I get 1. And I do that, e to the x is the nicest thing to take the derivative of, right? Oh, I just want a cubic. I'm sorry. I thought it was. Yep. So I want a cubic polynomial. So I want that to happen for both the first derivative, the second derivative, the third derivative, and then I can stop. Now, at the same time, I am going to realize that my polynomial, think of it as a polynomial function. So my polynomial function, we already have, it's up here. What would happen if, well, let me rewrite this. Actually, let me rewrite it this way. Sorry. Trying to get good spacing. So my polynomial function is right here. Notice that when I plug in 0 into that polynomial function, what I get out is just a sub 0. A sub 0 because all three of these other terms will go away. Now take the first derivative of that polynomial function. The first derivative with respect to x, obviously, is equal to, well, a sub 0 is constant. The derivative of a sub 1 times x is just going to be a sub 1. The derivative of a sub 2 x squared is going to be 2 times a sub 2 times x to the first. And the derivative of a sub 3 x to the third becomes 3a sub 3 x squared. Notice what happens when I plug in 0 into that polynomial function. So I'm plugging in 0 into the first derivative. The 2a2x and the 3a3x squared will go away. And in that case, we'll just be left with a sub 1. Now you might think, oh, you might guess a sub 2 is what you're going to get with the second derivative. That is not the case. Notice we're going to have some coefficients here. In the second derivative, what we would get is 2a sub 2 plus, this is going to be 3 times 2, which gives me a 6a sub 3 x to the first. And so when we plug in 0 into the second derivative, we get 2a2, 2a sub 2. Whoops. And then we take the third derivative and do the same. Oh, hit a wrong button there. So third degree, third derivative. All right. And that one's going to give us just 6 times a sub 3. And obviously that's constant, so that when we plug in 0 into our polynomial, we're going to get 6a3. Now we want this function value to be equal to this polynomial value at all of the correct derivatives and at the correct places. So since f sub 0 is equal to 1, I want 1 equal to p sub 3 sub 0, which tells me that a sub 0 is going to have to be 1. So that's it. The f of 0 has to be equal to p sub 3 of 0. I know f of 0 is 1. I know p of 3 of 0 is p3 of 0 is a 0 in my general expression. So that means that the constant term in p3 has to be 1. I'm going to write that over here. 1 has to be the constant term. 1 equals a sub 0. Now, the same thing is true for the first, second, and third derivative. We're just going to set those equal to a1, 2a2, and 6a3 respectively. I have done that. So when we set f prime of 0 equal to p prime of 0, I get 1 is equal to a1. That gives me the coefficient of the x term. When I set the second derivatives equal, I get that 1 is equal to 2 times a2. That means a2 needs to be a half. And when I do that for the third derivatives, that forces 1 equaling 6 times a3. So a3 has to be 1/6. Now I have the coefficients that I was looking for in my polynomial. I knew my polynomial was going to look like this. Now I know what those coefficients are. And we call this the Taylor polynomial of degree 3. So a sub 0, like we said, is the number 1. A sub 1 is also the number 1. A sub 2 is the number 1/2, and A sub 3 is the number 1/6. Let's try to make this a little bit more compact. There we go. Again, you can call that P sub 3 or P sub 3 of x. And that polynomial is going to be a third degree polynomial, which approximates f of x equals e to the x very closely around c equals 0. In other words, around x values which are close to 0. Let's graph both f of x equals e to the x and this polynomial to see how closely we got. Now I've graphed both of these. The curve f of x equals e to the x you see here. Let me make sure our steps are correct on that. I want to be careful. Obviously, it goes through the point 0, 1, just like we had said. When you plug in 0, you get 1. And now let's take a look at this cubic polynomial, this third degree polynomial. Notice that it also goes through the point 0, 1. And when we're pretty close to x of 0, it's really hard to even see a difference between the polynomial and the function. Obviously, when we get far away from that, if we're at x equals -3, the function and the polynomial are very far apart. But when we're close to 0, this polynomial is going to approximate the function really well. And again, if you'd move out to the right, you'd see that as you move out to the right, you get pretty far apart as you move further and further away from 0. Move towards the left, you get further apart. Move towards the right, you get further apart. But when we're close to 0, it's a pretty darn good approximation. And that's nice because if we have to plug in 0.25 into e to the x, it's actually way easier to plug in 0.25 into that polynomial function if I'm trying to do it by hand. Because who knows the e to the 0.25 power? We can, with calculators, we can get a really good approximation quickly, but if I had to do it by hand, that'd be pretty tough. Now, the question arises, what would happen if instead of centering this at 0, what if I wanted to center this at 2? So obviously, we have a nice Taylor polynomial. We have a cubic polynomial approximation for e to the x centered at c equals 0. But we saw when we plugged in numbers that are kind of far away from 0, it's not a very good approximation. So what if I wanted to center it at a certain other number, like 2, because I wanted to figure out what e to the 2.03 was, for instance? So here's the trick. The trick with centering this polynomial at a different value is instead of using just x as the variable, I use x minus 2. So we're going to take each x and replace it with an x minus 2. The reason that's going to work nicely is because this is also going to be third degree, because when I expand this out, the highest degree is going to be 3, Highest degree here is going to be 2. Highest degree here is going to be 1. But when I start plugging in 2 into this type of polynomial, I get lots of zeros. So we'll go ahead and do that momentarily. First, before we start plugging in 2 into the polynomial, we should start by taking derivatives of the function I'm trying to approximate. Those, in this case, are all e to the x. When I plug in 2 there, I'm just going to get an e squared. Now, e squared is not nice to deal with. It's not super nice to deal with, but it's a lot easier to deal with e to a whole number exponent than dealing with e to like a 2.03. So we plug in 2. Again, this is all if I'm doing this by hand, which is what people were doing when this was first developed. So e squared in every single value and in every single derivative, we get the e squared. Now, instead of using this polynomial, what we're going to do, oh, let me spread some things out first. Instead of using this polynomial, I'm going to replace every x I see with an x minus 2. Okay. When I plug in 2 into that, I get an a sub 0. Notice that when I plug in 2, this becomes 0, this becomes 0, this becomes 0. Now when I take a derivative, watch what happens. Essentially, everywhere I already had an x just becomes an x minus 2, because when I take the derivative of x minus 2, 1 would come out front. 1 times a1 is a1. And then x minus 2 is raised to the 0th power. Since the inside function has derivative 1, when I multiply times the derivative of the inside function, it doesn't change anything. Same thing on the second term. 2 comes out front. I get 2a2 times x minus 2 to the first. Derivative of the inside function is 1. 1 times anything is itself. 3 comes out front. 3a3 x minus 2 squared. When I plug in a 2, I get a1. Then let's take the second derivative. Second derivative, well, derivative of a1 is 0. Derivative of this is going to be just the coefficient of 2a2. Derivative of the third piece, the third term, is going to be 2 times 3 times a3. 2 times 3 is 6, so you get 6a3. When I plug in 2 to that, I get 2a2. And then lastly, when I take the derivative, the third derivative, I would get 6a3. So when I plug in 2, I get 6a3. Notice that these are the same as we had in the last example. In fact, they're always going to be the same. You can always figure out how to take the derivatives. And if we want to do a fourth derivative and a polynomial of fourth degree, what would happen is after you did the you'd have to do the fourth derivative. The exponent of 4 comes down first, then 3, then 2, then 1, and then you'd get 24. A to the fourth is the fourth derivative. a sub 4, excuse me, not to the fourth. So now we're ready to set all of these equal. F of 2, F prime of 2, F second prime of 2, E2, all of those have to be equal to the specific values, A0, A1, 2A2, and 6A3. Let's write that here. I've just done the computation, so that's what I want to throw up there, but I think they're pretty straightforward. Since f of 2 and the polynomial at 2 have to be equal, e squared has to be a sub 0. Since f prime at 2 and the polynomial first derivative of the polynomial at 2 have to be equal, we can say e squared has to be a 1. Second derivatives have to be equal. We can say e squared has to be 2 times a2. That means e squared over 2 is a2. And then this one is e squared equals 6a3. So we get e squared over 6 equals a3. So what's that mean? My Taylor polynomial of degree 3 has to be centered at 2. Well, first thing I'm going to do is say my constant has to be e squared. Coefficient of x term has to be e squared. Now we're not using x, rather we're using x minus 2. We get e squared over 2 times x minus 2, quantity squared. And then e squared over 6 times x minus 2, quantity squared. Quantity cubed, excuse me. So that's what happens if we center this at 2. Notice that whole polynomial is e squared times a lot of these coefficients are the same as in our previous one. So very, very similar. Let's go ahead and graph that and see what that polynomial looks like as well. So I have that polynomial graphed here. And you can notice that when you go up to an x value of 2, that polynomial is really, really a very close approximation to my function when we get closer and closer to the x value of 2. So when I get closer and closer to the x value of 2, we have a pretty good approximation for the polynomial, or excuse me, for the function with the polynomial. Obviously, when we get further away from 2, like down here at 0, the polynomial and the function are not close. But at x equals 2, the polynomial and the function are, in fact, very, very close. And then obviously as you move away, if you moved up here, they'd be pretty far off. It doesn't look like that because I'm zoomed out so far, but they are pretty far off when you get up to some high x values. But right at 2, really nice approximation. So notice that our first polynomial was a pretty bad approximation when x was 2, the one we found earlier. But this new polynomial is a very good approximation when x is 2. The first one we found was a really good approximation of the function when x was 0, but the second polynomial we found was a really bad approximation when x is 0. So certain polynomials approximate well really close to certain values. In our first example, we found a polynomial that approximated really well, close to values which were 0. In our second, we found a polynomial that was approximating really well when our values were close to 2. Now, once you start seeing this pattern, that p sub 3 of 2 is just a0, p sub the first derivative at 2 is a1, second derivative at 2 is 2a2, third derivative at 2 is 6a3. This pattern can generalize. Let me write that down. So for a polynomial centered at C, I want the polynomial, well, again, polynomial centered at C, the way I wrote it, the constant term will be a0. That's what would happen when we plug in C. We get a0. When we take the first derivative, plug in C, we get a1. Second derivative, plug in C, we get 2a2. Third derivative, we get 6a3. The fourth derivative, excuse me, that would be a3, that'd be a4. We get 24a4 because that would come from taking the derivative of x to the fourth, we'd multiply the coefficient by 4. Then the derivative, we'd multiply the coefficient by 3, then by 2, then by 1. So that 24 is actually 4 times 3 times 2 times 1. And in general, if we do a kth derivative, let me put that in parentheses just so it looks like a derivative. Kth derivative, we're going to do k factorial as our coefficient of a sub k. Whoops, I forgot there's one more. Sorry. So kth derivative is going to be k factorial times a sub k. And that means each one of these things, since that has to be equal to the kth derivative of f when I plug in c, that means there's a very quick formula for finding the coefficient on each and every one of these. And in order to find the coefficient a sub k, all I have to do is create a fraction where it's the kth derivative plug in c and divide by k factorial. That's going to work for every single k that we can find, including all of these ones that we've already done. If you go back into the last two examples, you can confirm that if you'd like, but the coefficient's there. So now I don't have to go through all of this work of forcing myself to figure out what the coefficients are. Now I can just start and say, well, I know what these coefficients are. The a sub 0 is going to be what I get when I take the function and plug in my center. A sub 1 is going to be what I get when I take the first derivative of my function, plug in the center, divide by 1 factorial. A sub 2 is second derivative, plug in the center, divided by 2 factorial. Third coefficient is going to be third derivative, plug in the center, divided by 3 factorial. And that's precisely what we got. These e squared was plugging in f of 2, or f, in this case, the third derivative, plug in 2 into the third derivative of my function, divided by 3 factorial, which was 6. So these coefficients give me everything that I want. And now I can just find the derivatives that I need and then write my polynomial out fairly efficiently. Therefore, this becomes my Taylor polynomial of degree n. So the nth degree Taylor polynomial centered at C for function f of x is that formula. We're just adding up a bunch of terms where I take nth derivative, plug in c divided by n factorial times x minus c to the n. And we're doing that from n equals 1 up to the number, whatever that n is, if I want nth degree. Here, I didn't write divided by 1 factorial because 1 factorial is just 1. Here, I did not write divide by 0 factorial because 0 factorial is also 1. So 0 factorial is 1. I didn't need to write it down. 1 factorial is 1, so I didn't need to write that down. But some people would write divided by 1 factorial, divided by 0 factorial. But it's unnecessary because dividing by 1 doesn't change the value. So that's it. Kth derivative, plug in my center, divided by k factorial times x minus the center to the kth power each and every time from 0 up to the n degree I'm looking for. Now we call this a Taylor polynomial centered at C. Another term you'll hear often is Maclaurin polynomial. A Maclaurin polynomial is just a Taylor polynomial who is centered at 0, or which is centered at 0. So if we replace the c with a 0, then x minus c becomes just x. And we get the Maclaurin polynomial. You'll see that term on some subsequent slides. But Maclaurin polynomial is a Taylor polynomial centered at C of 0. Let's do an example now that we know what the Taylor polynomial is supposed to look like. We're going to find the third degree Taylor polynomial for f of x equals 2 to the x power centered at C of 3. Now, first thing I'm going to do is say my function is equal to 2 to the x power. And then I say, well, what's going to happen when I plug in a center it at 3? 2 to the third power is becoming 8. If I take the first derivative of the function with respect to x, I get, again, 2 to the x power, but now I have to multiply times natural log of 2. Notice that if you plug in 3 to the first derivative, you don't get just 8, you get 8 times the natural log of 2. Now 2 is positive, so don't have to put absolute values or anything. Now let's do the second derivative. Well, if I do the second derivative of f with respect to x, I'm going to get, once again, 2 to the x power, and then I have to multiply times another copy of natural log of 2. So essentially, I need to multiply it by natural log of 2. quantity squared, which means that if I took the second derivative and plugged in 3, I would end up with 8 times the natural log of 2 squared. I mistyped something just a second ago. I will fix it. This should have said natural log of 2 squared, not natural log of x squared. Excuse me. Yeah. When you take a derivative of something of base other than e, then you have to multiply times natural log of that base. So exponential derivatives here. If I do third derivative, excuse me, not third degree. So if I'm doing a third degree Taylor polynomial, I need third derivatives. Notice that we're just going to multiply by another copy of natural log of 2. So I multiply by another copy of natural log of 2, which gives me natural log of 2 to the third power. And then when I plug in the number 3, 2 to the third is 8, multiplied times natural log of 2 to the third power. So now I have my function value, my first derivative, my second derivative, and my third derivative. Now I'm ready to go and write that Taylor polynomial. So polynomial, again, it's degree 3, so often we put a subscript of 3. So we start with the function value, and then plus first derivative is 8 times natural log of 2. And I need to multiply that times x minus 3 raised to the first power. Then I take 8 times natural log of 2 squared divided by 2 factorial. 2 factorial is just 2 times x minus 3 squared. If you want to simplify this, you can, but I'm making a point here, so I'm going to write it in expanded form. Third derivative is 8 times natural log of 2 cubed. I'm going to divide that by 3 factorial, which is a 6. And then I'm going to multiply times x minus 3 to the third power. Let's see if I can. There we go. So there we go. 8 plus 8 natural log of 2. I could divide by 1 factorial here. I don't write that. Times x minus 3 because we centered at 3. And again, 8 over 2 factorial, that's just 4. So you can call this whole thing 4 times natural log of, times natural log of 2 squared. And then 8 over 3 factorial, that's 8 over 6, which is 4/3 if I reduce. So if you want to reduce, this reduces to that. I tend not to. I tend to leave it this way. Although when I write my answers, a lot of times I do reduce. I shouldn't say that. So it goes both ways, I guess. But that's the third degree polynomial we were looking for. And that would be a very good approximation of 2 to the x power when we're at x values that are really close to 3. And again, you may think, well, why do I care about all of this stuff? We have access to our calculator, so we can just plug in 3.01 and get a good approximation with our calculator. Again, historically, people didn't have that. So if you're plugging in 3.01, you get 2 to the 3.01, and that's pretty tricky to do because what's 2 to the 0.01 power? Again, tough to find. But natural log of 2, we can get a pretty decent approximation for. All of these other numbers are whole numbers, and then when you plug in something like 3.01 into x, then this just becomes 0.01, some decimal. This becomes 0.01 squared. This becomes 0.01 cubed. So it's pretty easy to deal with. I do want to note that I've been talking about being easy to deal with in the sense of getting good approximations. We will see some other things a little bit later, which will connect uh, the infinite series with these Taylor polynomials. And there's some interesting results that we can get using Taylor polynomials and infinite series. And so it's not all just approximations, but in this section, there'll be a lot of approximation stuff. So let's do the same thing. Let's find a fifth degree Taylor polynomial for the natural log of x centered at c equals 1. And then let's calculate p sub 5 of 1.05 and f of 1.05. As always, I start, so we're going to center this at 1. F of x is the natural log of x. We're always going to be plugging in 1, so that's pretty straightforward. When I plug in 1 into natural log, I get a 0. So natural log of 1 becomes 0. The derivative of natural log is 1 over x. Or, as I could write it, x to the negative first power. And when you plug in 1 there, you just get 1. Second derivative, it's probably easiest to see here. You bring the 1 out front, and then it's an x to the negative 2. So we get negative 1 x to the negative 2, which is also the same thing as negative 1 over x squared. Let's put the negative in the numerator instead of out front of the fraction. But we can see here that the second derivative, when you plug in 1, becomes negative 1. I said plug in 1 earlier too. Now, what's going to happen with the third derivative? Well, the third derivative of my function is, well, let's do it this way. Negative 2 times negative 1 is just a 2 times x to the negative 3 power, which is a positive 2 over x to the third power. And so the third derivative, when I plug in 1, becomes 2. Only 2 derivatives left. The fourth derivative is negative 6x to the negative fourth power, or in other words, negative 6 over x to the fourth. When I plug in 1, I get a -6. So I have 0, 1, -1, 2, -6. Notice that they're kind of, from here on out, they're kind of alternating back and forth between positives and negatives. And also this 1, 1, 2, 6, that's factorials. So let's do fifth degree. This is not f to the fifth power, but rather f, the fifth derivative of f. A lot of times people put that in parentheses if there's any question about it. I'll get a positive 24x to the negative fifth, or in other words, 24 over x to the fifth. So fifth derivative, when I plug in 1, gives me a positive 24. Now that I have that, my fifth degree polynomial, think of it as a fifth degree polynomial function, is going to be 0. Oh, this was centered at 1. Don't forget, this is centered at 1. So 0 plus 1 times x minus 1 to the first power. Plus, now we're going to have a fraction of -1 over 2 factorial x minus 1 to the second power. That -1 came from the second derivative when I plug in 1 was -1. So that's where I get the numerator there. Denominator is going to match up with the exponent. So in the next one, denominator is going to be 3 factorial. We're going to have x minus 1 raised to the third power. And then in the numerator, we're going to have the number 2, which matches the third derivative at 1. In the next case, my numerator matches the fourth derivative. So my numerator would be -6. And then my denominator would be 4 factorial. And that means I need to multiply by x minus 1 to the fourth power. And then lastly, fifth is 24. Excuse me. Fifth derivative, when I plug in 1, I get 24 over 5 factorial. And then we get x minus 1 raised to the fifth power. This polynomial is the fifth degree polynomial. I'll force that to be on one line here. All right, so there it is. That's forced to be on one line. Now I can simplify this. Obviously, I don't need to write the 0. Don't need to write the coefficient of 1 if I don't want to. -1 over 2 factorial is just -1/2. 2 over 3 factorial is 2 over 6. 2 over 6 is also 1/3. So we can write this as 1/3. -6 over 4 factorial is -6 over 24. And -6 over 24 is actually 1/4. Or I should say -1/4. 24 over 5 factorial is 24 over 120. 24 over 120 is 1/5. So simplified, we get this. We get x minus 1, coefficient is 1, then -1 half x minus 1 squared, and then positive 1/3 x minus 1 to the third, and then negative 1/4 x minus 1 to the fourth, and then positive 1/5 x minus 1 to the fifth. So that's our fifth degree Taylor polynomial, simplified. Now, it also asks us to approximate at 1.05, both the function and the polynomial. This is something I will utilize my calculator for. When I plug in 1.05 into the function, that's the natural log of 1.05. When I plug that into my calculator, natural log of 1.05 becomes about, I'll write all of the decimals, all the decimals that my calculator gives, 0.0487901642. Now, when I do the polynomial of degree 5, and I plug 1.05 into that, one of the nice things is notice that every time you plug in 1.05 and then subtract 1, you just get 0.05. So we have 0.05 minus 1/2 times 0.05 squared. This is plus 1/3 times 0.05 to the third power. That's minus 1/4 times 0.05 to the fourth power. And then plus 1/5 times 0.05 to the fifth power. When I did that, again, I'm not writing out every step here, but when I did that, I ended up getting 0.0487901,667. Notice how close those two values are. If I put them right under each other, they're exactly the same until we get out to the last two decimals on my calculator. This shows that close to the value of x value of 1, my polynomial approximates my function pretty well. So in order to find these Taylor polynomials, take derivatives, and then one thing they can be used for is approximations. Other insights can be gained as well, and we'll get to those a little bit later. Now let's stay with this same function for just a moment. Let's take natural log of x. Let's still center it at c equals 1. But what if we wanted to find a third degree Taylor polynomial for this function? And then try to approximate that at 1.05. So doing the approximation with degree 3 polynomial instead of a degree 5 polynomial like we did in example 4a. Now, I always like to not reinvent anything. So if I want to find the degree 3 Taylor polynomial and then find p sub 3 at 1.05, notice that all of the work that I previously have done to find the degree 5 Taylor polynomial would be good. I just don't need the fourth and fifth derivatives now. And in the same way, I could just change degree 5 to degree 3 by lopping off the degree 5 term and the degree 4 term. If I wanted to find the degree 3 Taylor polynomial, that's all I'd have to do. And by the way, if I already found degree 4, I could just take another, or excuse me, degree 3 and wanted to find degree 4, I could simply take another derivative, plug in 1, and then tack on a term. So here we lopped off because we were decreasing in degree, but we could have also tacked on if we wanted to increase in degree. Now, if you plug in 1.05 into this degree 3 polynomial, again, same thing as before, except now we are degree 3 instead of degree 5. So I'm going to go ahead and do that. I got something pretty close to the old value, but it's a little bit different, 0.048791, and then 6667 as the calculator display. This would be a 6 repeating. But there you go. Notice that when we did this with degree 5, let me copy this one and compare. When we did this with degree 5, our approximations were just slightly better than when we did this with degree 3. So with degree 3, we're off out here at the 1, 2, 3, 4, 5, 6. Sixth decimal spot, we're off. With degree 5, I was off at the 1, 2, 3, 4, 5, 6, 7, 8, ninth decimal spot. So what's that tell us? Well, that tells us that when we go up degrees, we get slightly better approximations, which should be fairly obvious because we're forcing more and more derivatives to be the same. So as you go up in degree on your polynomial, you'll get better and better approximations in general. I want you to try this on your own. Find the fourth degree Maclaurin polynomial for my function of 10e to the 2x, and then do the same thing on the next, but rather the fourth degree, try the sixth degree Maclaurin polynomial for that function. And then with both of them, plug in 0.05 and see how well that matches the function value at 0.05. So do the fourth and sixth degree polynomial. Push pause on the video if you're trying that. If you're not going to try that, then again, I'll give you a couple of seconds to push pause. But if you're not, then I am going to just do it. All right, so I'm going to do it. I'm going to start by just taking derivatives. And When you take a derivative of e to the 2x, you get 2 times e to the 2x. So the first derivative would be 20 times e to the 2x power. Then the second derivative would be 2 times that. So you'd get 40 times e to the 2x power. And then the third derivative, you would get 2 times that, or 80 times e to the 2x power. And then the fourth derivative would give you 160 times e to the 2x power. Now, this is supposed to be a Maclaurin polynomial. If you remember, Maclaurin polynomials are those which are centered at 0. So I'm going to plug in 0. Well, that gives me e to the 0th power, which is a 1. When I plug in 0 into the original function, I get a 10. Into the first derivative, I get a 20. Into the second derivative, I get a 40. Into the third derivative, I get an 80. And into the fourth derivative, when I plug in 0, I get 160. Now I'm ready to create my Maclaurin polynomial of degree 4. So my Maclaurin polynomial of degree 4 is going to be, again, start with function value 10 plus 20 over 1 factorial times x to the first power. This is Maclaurin, so x is just x minus 0 is just x. Second derivative would be 40 over 2 factorial x squared. Then third derivative would give me 80. Divide that by 3 factorial times x to the third. And then fourth derivative gave me 160. I divide that by 4 factorial and then times x to the fourth. That's my fourth degree Maclaurin polynomial. Or you could have also said the fourth degree Taylor polynomial centered at 0. Now I can do approximations. Actually, let me do a simplification here before I do my approximations. So the polynomial, obviously I've written it in a way where we have factorial. 40 over 2 factorial is 40 over 2, which is 20. 80 over 3 factorial, that's 80 over 6. If I take 80 over 6, I get either 13 and a third, or you could do 40 over 3. That's how I'm going to write it. I'm going to write it as 40 over 3. And then 160 over 4 factorial. Well, 160 divided by 24 gives me 6 2/3. But we can, again, make a fraction. So that's 20 over 3 if we simplify that. So when I plug it into my calculator, I'll probably use this version. Again, we're plugging in 0.05 or just 0.05 into the function. That's 10 times e to the 2 times 0.05. When I plug that into my calculator, I got about 11.05. I'm going to write all of the decimal places just to say what's going on. When I do that for my polynomial of degree 4, Takes a little bit longer to plug it into your calculator because you have more things, but it's a pretty straightforward process. I did that on my own and I got 11.05170833. Again, notice it's pretty close, little bit off after you get down past 5 decimal places. So there we go. That's the Taylor or polynomial of degree 4 centered at 0, which is also called the Maclaurin polynomial. If I'm going to do degree 6, I'm going to keep all of this work and just add on a couple more terms. So if I want to do a degree 6 Maclaurin polynomial, no sense in doing this all from scratch. What I would do is I would just take the fifth derivative, there is going to be 320 e to the 2x. And then that fifth derivative when I plug in 0 becomes 320. Pretty obvious what's going to happen with the sixth derivative. Sixth derivative becomes 640 e to the 2x. And when I plug in 0, I get 640. Takes longer to type out than it actually does to figure out. And then I say, let's just add on a couple of terms. So let's add on a fifth degree. So that would be 320 over 5 factorial times x to the fifth, and then add on a 640 divided by 6 factorial x to the sixth. 320 over 5 factorial. I will type that into my calculator. Five factorial is 120, excuse me, if I didn't say that. That gives you 8/3. So we get 8, oops, 8/3 x to the fifth. And then 640 divided by 6 factorial gives you 8/9. So 8/9 x to the sixth. And there you go. If I want to do my approximations, I've already plugged in 0.05, but you can also plug in 0.05 into the polynomial. I've already plugged it into the function. Now let's plug it into the polynomial. A lot of my work has been done for me. I can just tack on those last two terms. And when I do that, I get 11.0517 0.70918. Now, I want to be clear. This is what the calculator gave me out. If I would have went out more decimal places, eventually these two values would have differed by a little bit. But as we can see, out to 8 decimal places, these two are the exact same numbers. So this gives me a very good approximation when we are close to 0. All right, so now let's do another. Example 6 says find the 6th degree Taylor polynomial for c equals 4 with this function, 2 over x minus 5. And then do a couple of approximations. Approximate at 4.01 and then approximate at 4.1. So when we're really close to 4 and when we're pretty close to 4. All right, if you want to do this on your own, obviously pause the video, but I'm going to jump right into it. So 2 over x minus 5 is the same thing as 2 times x minus 5 to the negative 1. I'll take the derivatives first. If I take a derivative of that, negative 1 times 2 is negative 2, and then I lower that exponent by 1. So I get negative 2 times x minus 5 to the negative 2 power. If I take the second derivative, what I get is negative 2 times negative 2, that's a coefficient of 4, times x minus 5 to the negative 3. If I do the third derivative, I end up getting a negative 12 times x minus 5 to the negative 4. If I do a fourth derivative, I end up getting a positive 48 times x minus 5 to the negative 5. Fifth derivative, take negative 5 times 48, and that gives you negative 240. So you get negative 240 times x minus 5 raised to the negative 6th power. And then when you multiply that times a negative 6, that negative 240 by a negative 6, you get a positive 1,440 times x minus 5 to the negative 7th power. When you plug in 4, basically you get a negative 1 in this parentheses. So when I plug in 4, 2, I'm getting 2 times negative 1 to the negative 1 power. That's like 2 divided by negative 1. So that's negative 2. When I plug in 4, I get negative 2 times negative 1 to the negative 2 power. That's like dividing by negative 1 squared. Negative 1 squared is positive 1, so you get negative 2. When I plug in 4 here into the second derivative, I get a negative 4. When I plug in 4 into the third derivative, I get a negative 12. When I plug in 4 into the fourth derivative, I get a negative 48. Fifth derivative, I get a negative 240. And sixth derivative, I get a negative 1,440. That takes the longest time. Now we're centering this polynomial at 4. So it's a Taylor polynomial centered at 4 of degree 6. It's going to be pretty long. That's okay. We start out with the number -2. That's my actual function value. Then first derivative is -2 times x minus 4, since we're centered at 4, to the first power, minus 4 over 2 factorial x minus 4 squared, minus 12 over 3 factorial times x minus 4 raised to the third power, minus 48 over 4 factorial times x minus 4 raised to the fourth power, minus 240 over 5 factorial times x minus 4 raised to the fifth power, and then minus 1,440 divided by 6 factorial times x minus 4 raised to the sixth power. Each of those coefficients can be simplified. I'm going to keep this on 2 lines. Let's simplify as best we can. 4 over 2 factorial is 2. 12 over 3 factorial, that's 12 over 6. That's also 2. 48 over 4 factorial, that's 48 over 24. That's also 2. 240 over 5 factorial, that's 240 over 120, which is also 2. And then 1440 over 6 factorial, 6 factorial is 720, so 1440 over 720 is also 2. Notice that this just becomes 2. That was that numerator. So -2, -2, negative, all these -2's times x minus 4 to whatever power. Now let's plug in 4.01 into here. Let's do the same for my function. My function, remember, was 2 divided by x minus 5. So if I plug in 4.01, that's a pretty easy calculation to do. 2 divided by 4.01 minus 5. Make sure you do the denominator before you do 2 divided by that. I get, as a decimal version, -2.02020202. That's the calculator display. Let's do this one. Let's plug in 4.01 while we're at it. 2 over, I plugged in 4.01, just 4.1. Plug in 4.1. I get -2 point, and then lots of 2's repeating. Oops, forgot to put the equal sign. There you go. So that's what I get. Now let's plug in those two values into this polynomial. I'll do that on my own. Interestingly enough, when I did that, with 0.01, I got the exact same value on my display on my calculator. Now, I do have to sort of put a fair warning on this that this does not mean I got the exact same answer. It just means it rounded to the same number. If I would have went out further, then it would have been different eventually. When I plug in 4.1, I ended up getting negative 2 point and then only 6 decimals worth of twos. Here, I got out 9 decimals worth of twos. And then after the 6, it's basically all zeros. So that's why your calculator display doesn't have that. Now, I want to point something out. When we plug in 4.01, I got a better approximation than when I plugged in 4.1. The reason for that is because I was closer to the center when I plugged in 4.01 compared to plugging in 4.1. So the closer to the center we are, the better approximation we have. These last three examples have shown us that we do get pretty good approximations around the center. Now, there is a formula that exists to show you how far off your Taylor polynomial will be from your original function at certain values. I typically don't use that formula for very much, but we should know that the higher degree Taylor polynomials will give better estimates. So a degree 5 Taylor polynomial will give a better estimate than a degree 3 Taylor polynomial at the same value. Again, this is in general. And degree 7 Taylor polynomial will be, when I plug in a value, will generally have a better estimate than a degree 5 Taylor polynomial. So higher degree polynomials generally give better estimates, again, assuming we're plugging in the same values. The other thing we should know is that the closer we are to the center, the better our estimates will be. I'll say that again. The closer we are to the center, the closer the x values are to c, the better the Taylor polynomial is going to estimate our actual function. So that is a very good thing. We know that polynomials, when we have these, we can create these polynomials that give really good estimates for our function around certain center points. And our function may be a rational function like we had in example 6. It can be exponential functions like we had in example 5. We had a natural log value earlier. We had other exponential functions. And again, we can get really good estimates with polynomials. Let's do a Maclaurin polynomial for trig functions. Let's do sine and cosine. These are actually paired quite nicely. So we'll find the 6th degree Maclaurin polynomial for sine, and then we'll do the same thing for cosine. I'll call f of x sine and g of x cosine. If you want to try it on your own, then by all means, try this on your own. I'm going to start dealing with sine first, and we'll again see why that is. So the function is sine. That means that the first derivative is cosine. That is cosine of x. The second derivative, that is the derivative of cosine, would be negative sine of x. And then the third derivative, we would get negative cosine of x. The fourth derivative, we would end up with a positive sine of x. The fifth derivative, that is the derivative of sine, would be positive cosine of x. And then the sixth derivative would be a negative sine of x. Now, Maclaurin means I'm centering this at 0. So when I plug in 0 to sine, every time I plug in a 0 to sine, I get out a 0. Every time I plug in a 0 to cosine, I get out the number 1. So notice we're going to have 0 when I plug into sine, 1 when I plug into cosine. Negative sine is going to give me 0. Negative cosine is going to give me negative 1. Sine is going to give me a 0. Cosine is going to give me a 1. And then negative sine is going to give me a 0. So that's what we have. When I look at the 6th degree Taylor polynomial centered at 0, also known as the 6th degree Maclaurin polynomial, that means I'd have to start out at 0 plus, this is 1 over 1 factorial times x to the first, plus 0 over 2 factorial x squared plus negative 1 over 3 factorial x to the third plus 0 over 4 factorial x to the fourth plus 1 over 5 factorial x to the fifth plus 0 over 6 factorial x to the sixth. Simplifying this, if I take this polynomial and if I simplify the coefficients, actually I get a lot of zeros. So I end up with 1x plus negative 1 over 6 x to the third plus 1 over 120 x to the fifth. So I end up with just 3 terms, and it's a pretty nice polynomial to deal with. Now here's why I wanted to do sine and cosine at the same time. Notice that f prime is actually just g of x. And then my first derivative would be the second derivative of cosine. So the first derivative of cosine is the second derivative of sine. Hopefully that all makes sense. So when doing g of x, and this again was for, let me just write this, for f of x equals sine of x. So that was for the sine of x. If I was going to do the exact same thing for cosine, I essentially just need to do one more derivative. Take the sixth derivative, and now take the seventh derivative. So we go seventh derivative, negative sine has derivative of negative cosine of x. When I plug in 0 into the seventh derivative, I get a -1. And I just moved the derivatives down 1 because now, again, this 1 will be my g of 0. This 0 will be my first derivative of g at 0. And this -1 will be my second derivative of g at 0. And so on and so forth. Third derivative 0, fourth derivative is 1, fifth derivative 0, sixth derivative is -1. So if I want a polynomial of degree 6 that represents cosine, I'd start at 1 plus 0 times x to the first minus, or I should say plus, we'll do it this fraction way, -1 over 2 factorial x squared plus 0 over 3 factorial x to the third plus, that's third, +1 over 4 factorial x to the fourth plus 0 over 5 factorial x to the fifth plus -1 over 6 factorial x to the sixth. And again, when I simplify that, pretty easy to simplify because the numerators are all ones, -1s, or zeros. Cancel out the terms with the zeros as the coefficients, and then I will rewrite my denominators without the factorial piece. So -1 over 2 factorial is like -1/2. 4 factorial is 24. 5 factorial is 120, but that's going to go away. 6 factorial is 720. And I just get these 4 terms. Interestingly enough, as you can see, this degree 6 polynomial only picks up even powers of x. Again, this one was 4 cosine. So for cosine of x, we just picked up the even powers for my Taylor polynomial, centered at 0. For sine, I just picked up the odd powers. If you remember about sine and cosine, sine was an odd function. And so, interestingly enough, odd functions, we're just picking up the odd powers on x when we centered at 0. And cosine was an even function, and we're just picking up the even powers of x when we center at 0. If you center it someplace else, then bets are off. But centering at 0, this is what we get. So we can find a Taylor polynomial for sine and a Taylor polynomial for cosine centered at 0. Those are also known as Maclaurin polynomials for sine and cosine. So here we found, again, the Maclaurin polynomial for sine and cosine. Now, we've been doing this for functions that are trig functions. We did this for a rational function. We did this for an exponential function. We've done this for natural log. We've done this for other exponential functions. And so we've done this for a lot of functions that don't start out as polynomials. And we saw the Taylor polynomial for each of those cases. It's very, very interesting that we can get a polynomial that approximates each and every one of those weird looking functions. And there's a lot of different functions. We can get a polynomial that approximates those pretty well at certain values of x. So let's do one more example. This is example 8, which asks us to find the 5th degree Taylor polynomial centered at 1 for a polynomial function. So this is a standard quadratic function, x squared plus 5x minus 3. And we want to find the 5th degree Taylor polynomial at c equals 1. All right, so this polynomial function is obviously x squared plus 5x minus 3. And the derivative of that is obviously 2x plus 5. And the derivative of that is 2. And then after that, every derivative beyond the second derivative is going to be 0. When I plug in the x value of 1, let's try to make this a little bit prettier here. I'm going to get 1 plus 5 minus 3. So I get a 3. Into the first derivative, I get a 7. Second derivative, I get a 2. And then beyond that, everything else is 0. Notice what that does. My 5th degree Taylor polynomial will be equal to 3 plus x minus 1, excuse me, 3 plus 7 times x minus 1 to the first power plus 2 over 2 factorial times x minus 1 to the second power. And then after that, it's all 0. So 0 over 3 factorial x minus 1 squared plus 0 over 4 factorial times x minus 1. Oh, I'm sorry. I miswrote that. X minus 1 to the third over there. Now it's x minus 1 to the fourth. And then 0 over 5 factorial times x minus 1 to the fifth. There we are. Obviously, if I wanted to simplify this, the 5th degree Taylor polynomial centered at 1 would be just 3 plus 7 times x minus 1 to the first plus 1 times x minus 1 squared. I will save you a lot of the work there. Basically, interestingly enough, so this is how I would finish writing it in general, usually. But in this case, I'm going to expand it out just to show you what happens. 7 times x minus 1 is 7x minus 7. And then when I expand out x minus 1 squared, I get plus x squared minus 2x plus 1. Now, when I combine like terms, what we see here is that this fifth degree polynomial, which is actually just a fourth degree, or excuse me, not second degree polynomial because every derivative being 3 and above gave me 0. I got x squared by itself. 7x minus 2x gave me a 5x. And 3 minus 7 is minus 4, plus 1 is minus 3. Notice that that was the exact same polynomial we started with, which isn't surprising. We're saying what is the best polynomial of degree 5, technically, or less that approximates this polynomial? Well, the degree 5 or less polynomial that best approximates this quadratic polynomial is going to be the quadratic polynomial itself. So if we do a Taylor polynomial on a polynomial of smaller degree than the degree we're looking for on the Taylor polynomial, then we'll get back the polynomial itself, albeit in maybe a different format. And by the way, this wouldn't just approximate it well, it would approximate it perfectly. In fact, you would get the exact same values here for the function and the polynomial because they are the same thing. And that's a little bit different from our previous cases. Like when we did cosine, we got this polynomial. When we did sine, we got this polynomial. These would approximate well around 0 because we centered it at 0. But if you get too far away, then they don't approximate really well. So just as we haven't looked at this before, but the polynomial approximation of sine for the, technically it's 6th degree, but it's a 5th degree polynomial, gives us same value at the origin. And then you can see as we start moving away, we're following this curve pretty closely with the polynomial. The polynomial, after you get to about -3 or so, really flies away from sine. And when you get to like +3, it starts really shooting up away from the sine curve. But in this little section, from essentially -π/2 to +π/2, it's doing a really good job at approximating the sine curve. And so that's what it looks like. So that's the big idea of Taylor polynomials. Anytime I have a function, I can create a Taylor polynomial centered at some value c for that function. And I can get the polynomial by taking my function value evaluated at my function evaluated at the center, and then all of the derivatives, kth derivative evaluated at c divided by k factorial times x minus c to the k power, all the way from 1 up to n, whatever degree I want. So that's it for this section.